we're doing counting. We're reviewing that. And last time we introduced two counting principles. And the first one was, if you have, we're counting choices. You have compound objects, like you have a sequence of things you want to know how many choices do you have to make a certain structure, like a list of items. So, and the two principles we had were that if you have independent choices, right, then, so for example, if to make the final set of items, you had N1 choices and then N2 choices, the total number of choices was going to be N1 times N2, okay? So the idea here was, now let's see in terms of what is this idea. Let's say that you have all your items are some big set, right? Like this. This is a set of items you want to count. And let's say that you can divide this up into N1 segments, right? So these are subsets that don't have any overlap, but that add up to be the whole thing, right? And then let's say that each one of these has N2 items in it. Well, the total number of items that you have in the set S is going to be N1 times N2. Okay? So, but thinking about it as choices makes it easier to sort of deal with. So, for example, if I want to know how many scrambles, if I had like Scrabble tiles for the letters S, A, oh, let's see. Oh, how about this one? You had the letters cats, and you want to know how many sequences. If I have the Scrabble tiles for C, A, T, and S, how many scrambles, how many different ways of rearranging this are? And the method is you divide all, you say, okay, I can have all, there's going to be a whole bunch of sequences that start with either C, A, T. The issue is not the answer. The issue is the method of getting there. So it doesn't matter what the answer is. Okay, so I can choose either C, A, T, or S for this first slot. So I put up here, I have 4 choices, right? Then here I have a second slot because I'm going to be, and I can say, well, whichever one I chose, like if I chose the C here, I would have the A, T, and S, right? So I don't know what those choices, I don't know what letters I'm going to have, but I know there's going to be, I have a choice of 3 of them, right? So if I put C here, I would put C in the first one, I could choose any of A, T, or S. If I put A here, I'd have C, T, or S. If I put T here, I have CAS. If I put S here, I have CAT. So that's what, so this is sort of like up here, I'd have 1, 2, 3, 4 segments here in S. And this would be the sequences where I choose C is the first letter, then A, then T, then S, right? And then in each one of these, I would have 3 choices. These would be C with then A, T, and okay. So doing that, then I have to. So then the number of these 2 choices is going to be 4 times 3. That's because it's independent. My choices. There is a dependence of which letters there are, but the number of choices doesn't depend. I'm still going to have 3. Then continuing, I'm going to have only 2. When I choose this here, I'm only going to have 2 choices here, and then this is going to be 12 times 2. Then there's only 1 choice remaining, and I'm going to have 24 times 1, so that N here is going to equal 24, which is the same thing as 4 times 3 times 2 times 1. And because we have these, sometimes with a lot of numbers, we call this 4, put an exclamation point, which it's just a definition of what you mean by 4 times 3 times 2 times 1. Okay, so this is how the multiplication principle works. And there was a second principle, which was that applies to mutually exclusive choices. And that's if you could say, okay, my full set was I either have N1 over here or N2 over here, and I make, because I have to choose either one from here or one from here. These are mutually exclusive. There's no overlap. There's nothing in the middle. What I can do is I can say, well, the total number S here is going to be N1 plus N2. Okay, so you have this. This is if the total number of choices you have is for mutually exclusive ones. So, for example, if you go to a restaurant and you can say, order either for a given price, you can either have a sandwich or soup, and if there's 6 sandwiches and 7 soups, the different possibilities are going to be, I could either choose 6 of the sandwich, one of these 6 or one of these 7, and the total number of choices you have are 13, because you have 6 plus 7 equals 13, right? Because you can either choose it. That's different than if you went and you could say for a given price, you could have a soup and a sandwich, right? Because then the 2 choices would be independent. I could have any soup with any sandwich. I would have 6 times 7 is 42 choices, right? It's like you could use any of the 6 sandwiches with any of the 7 soups. So I'd have 6 times 7 possible meals. So those would be, so you can, depending with the choices, you could have, that would be, I could have one or the other or both. This is I could have one or the other, but not both. You know, they're mutually exclusive choices or independent choices that I have to make for both. Okay, so then we applied that to this thing here. We did 3-digit even numbers, right? We counted those. But let's go and do number 2 here on page 261. Which is how many integers between 4 and 100 that end with 3, 5, or 7 are there? So that means they have to be greater than 4 and less than 100. So why don't you think about it for the second, and then we'll see if you can. So here the question is, how can you sort this out with respect to the multiplication addition principle, sort of dividing all the possible numbers up into independent choices and and you'll probably intuitively divide it up into like mutually exclusive choices, then figure out independent choices. So this might involve, both, or it might involve just independent choices. So you have an answer, right? Okay, so good. So hang on to it while everyone else gets their answer. Yeah. And the other question is, have you analyzed how you did it with mutually exclusive independent choices? Okay, good. Excuse me? Okay. There's probably several ways to do this that might be different. So you have answers? You ready? Okay. Let me see. Well, there's different ways. There's probably different ways of doing this. For example, I can think that there are, you know that there's going to be, if they're less than 100, right? There's only 2 slots for the numerals, right? So, but this slot here has to be either 3, 5, or 7, right? Now, so here, if I have a 2-digit number, I can have 1 through 9, but then I also have here the possibility of just 3, 5, or 7 as single-digit ones, right? So I could say, well, there's 2 ways to do it. Either I could say, well, I either have these 3, right? Or I could say, well, I could put 1 through 9 and put a 0 here to indicate that this is just a single-digit number, right?
Second. No.
Well, it's integers between 4 and 100. So I guess, so there would be, well, it doesn't really matter, right? Because 100 isn't one of the ones, it doesn't end with 3, 5, or 7. So if it doesn't matter whether, but then the problem is though, that if we have a 0 here, see, this isn't quite right? Because if we have a 0 here, see, we don't have a 3, right? So the problem is we can divide it up into, see, the problem is that we can say, okay, either it has 2 digits, in which these are 1 through 9, or it only has 1 digit, and these are 5 and 7, right? Because I can have 5 or 7 single-digit ones, but I can't have 3. Over here, I can have a 3 because this is always going to be larger. So I can either choose to be over here or here. So I'm going to add. These are mutually exclusive choices to either go here or here, right? There's 2 choices here. So the only things with 1 digit are 5 or 7, but over here, I have 3 choices, 3, 5, or 7, and 9 choices, and these are independent. So the total answer is going to be, I think, 3 times 9 plus 2, which is 3 9s is 27 plus 2 equals 29. And Josh will tell us whether that's correct or not.
That is right.
Okay. So this is a way that you could use you could sort of divide it between, okay, I'm either going to do this or this. That's that's like multiply mutually exclusive. You could divide it up into different ways that are mutually exclusive. Like you could count, it wouldn't be important here, but you could say count the numbers from 50 to 100 or the numbers from 49, less than 49, right? And that would, and then you can divide it up into many different ways, and that would not be efficient here, but that's okay. So questions about this, or do you guys get this? Excuse me? Okay, so what I want to do is I want to say, I see that there's a problem with a 3. That if this is 1 through 9, I can have a 3 here. But if it's not a 1 through 9, if there's only a single digit, I only have 5 and 7. So I just say, okay, I'm going to either going to choose one of these single digit numbers or a 2-digit number. Well, so I'm either here or here. So that's mutually exclusive. So I add the possibilities. So this is only 2 choices. But this one, I can put one of 3 numbers, 3, 5, or 7, that's the 3 choices, or 1 through 9, because that's the second numeral. So I'm going to have 9 times 3 9s is 27 numbers here, right? Plus 2 here is 29 numbers total. So I combined and used both the mutually exclusive principle and the independent choices principle. Okay, let's try number 3. You have 2 six-faced dice, right? So the first dice, there's going to be like 1, 2, 3, 4, 5, or 6, right? That's the red one. And the green one is also 1, 2, 3, 4, 5, or 6. So both of them are thrown. Okay, we want to know what is the number of possible outcomes if the sum, if we have red plus green has to equal, if the sum of the digits is either 3 or R plus G equals 6. Okay. So you want to sort of see, you understand the question, right? You roll the 2 dice and you want to know what are the possible outcomes of face-up numbers where the sum is either 3 or 6. So figure out what you think the answer is. Then I'll go and do it and we can see whether or not we agree. You have an answer. Good. Secret code. Okay. So what I'm going to prescribe is I want you to use, let's see, what kind of code we can have. You can make, let's see. So, Bassam, you have an answer? You're thinking. And John, you have an answer, right? Are you on the way? Okay. And you guys in the front, you guys have an answer, right? Okay. So let's see if we can, I'll go through and see if I can do this, you can compare. Okay, so having the sum 3 or 6 is a mutually exclusive choice, right? The sum is either 3 or 6. So let's say we can count how many ways can you get if the sum is 3, right? Well, you can either have a 1 or a 2 for red and green, or a 2 and a 1, right? So the number of choices for 3 here is 2 to get 3, right? What if I have 6? Well, I can have a 1 and a 5, or let me see, a 2 and a 4, or a 3 and a 3, or a 4 or a 2 and a 5 or a 1, right? So there's 1, 2, 3, 4, 5 choices here. So the total number of choices equals 2 plus 5 equals 7. Does everyone agree? Okay, so you can see how you can judiciously use these principles to divide it. That's so this stuff is a strategy. You're like, it's really a strategy that you're applying. Okay, the last one I think is a little bit, I keep going to, okay, so we've misordered the pages. This is 1. And this is 2. Well, that's going to be really confusing. This is page B. And this is page A. I did one page before. Okay, so let's go and do page C down here. And we're going to do number 4. How many strings of zeros and ones of length 6 are there? Now, I want you to not give you the number, but an expression. You know, like an arithmetic expression, if you calculate it, that represents how you get it. I'll show you in a second what you mean. So the question is, there's an expression that I could put into a calculator. So the question is, what expression do I put into a calculator to get the answer? Not the answer itself. For example, Josh, here's one for you. What if instead of length 6, there are 52,475 ones and zeros? Okay. Then what do you say the answer is? Then don't tell me, just think about it and fix your answer. This one, how many strings of what I put sequences? Like I can have, like for example, here's an example. I could have 0, 1, 0, 1, 0, 1. There's 6 ones and zeros. Another one could be 1, 1, 1, 1, 1, 1. Another one could be 0, 0, 0, 0, 0, 0. So how many of these are there? You have an answer? Okay. So, well, you have six slots, right? And for the first slot here, you have 2 choices, a 0 or 1. For this one, you have 2 choices, 2 choices, 2 choices, 2 choices, 2 choices, right? So the answer is going to be 2 to the 6th power, right? Because these are independent choices, so they multiply. Now, if you had 52,475 ones and zeros, the answer would be 2 to the 52,475. And we could put this in WX maximum and see if it would give us an answer. Right? But who knows?
Wait, what's that?
Well, if instead of 6, if we had 52,475 ones and zeros in our sequence, how many would there be? Would there be 2 raised to the power 52? And I guess my power is like, it's like so big it's trying to lift off and fly away. 52,475. Okay. This is a little different, right? I'm going to leave this one for you, and we'll come back. You can come back to it if you. How many strings of ones and zeros of length less than or equal to 5 are there? Right? So that's like strings of length. How many for 5? How many for 4? How many for 3? How many for 2? And how many for 1? Okay, so that's a different question. This one is just independent variables. You can see here that you could use mutually exclusive ones. You could count how many of length 5, how many of length 4, how many of length 3, and then just add them up. And that would be the expression. Okay, then there's question 6 too. Now, those are the general principles. Now we have a set of formulas that we're going to count sequences of objects, also arrangements, right? Sometimes called permutations, so I'll call them arrangements. This problem 1 or category 1 or type 1 is we're going to have 1 copy each of n items. So we have n items, but only 1 copy each, okay? Like n numbers or n Scrabble tiles. But we only have, and we have S equals n slots. Okay, so like if this is 3 items, and S equals 3 slots. Then we have 3 slots, and they're in, we could put any, so we could put any of the 3 items here. We have 2 left over, so we could put any of the 2 left over there, and we have 1 there, right? So the answer is going to be 3 factorial, right? This is the same problem with scrambles. So for n, the answer here is going to be n factorial, right? If I have n items, like 10 items and 10 slots, the answer is going to be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 10 factorial. Okay, so that's fairly straightforward. But what happens? Let's see. Okay, now there's a subcase here. What happens? See here, that's our answer here on page 263 is n factorial. But what happens if the items are not all distinct? Let's say, for example, that I have this name. And I want to know how many different sequences can I make of with this name, right? If I scramble these letters, like I've got 6 letters, right? So you can sort of see that there's a problem because they're not all distinct, right? Now, so here's the way to do this. What I do is I can say, well, there are 6 slots, so I'm gonna pretend that these are all different. So I'm gonna say here's 1 and 2, 1 and 2, 1 and 2. Okay, so I have n1 and n2. So then I can say, well, they're all distinct now. So I'm going to count how many there are. Well, there's going to be 6 choices here, then 5, then 4, then 3, then 2, then 1. So the answer is going to be 6 factorial, right? But in each sequence of these things, I've used, say, both ends, right? So for every sequence, I'm going to have an n1 in one slot and an n2 in some other slot. And I'm also going to have n2 and n1. So I'm going to have the number of sequences like that times 2, right? Because I'll have 2 copies of it. So what I need to do is I need to divide this out by 2 for the n's, but also 2 for the a's and 2 for the h's. So the answer is going to be 6 factorial. It's going to turn out to be 2 factorial equals 2, but it's going to be like this. So if you have repeated items, what you do is you pretend they're all distinct, count them, and then divide out by the overlap, right? And you hope that even though it looks like you're dividing out something, you can see that this is going to be 6 times 5 times 4 times 3 times 2 times 1 divided by 2, 2, and 2. Well, those go away. This becomes a 2 and this becomes a 3. So I have 3 times 5 times 2 times 3 times 1, right? Because this goes to a times 1, so to speak. This 4 went to a 2. So then this is like 2 5s is 10. 3 times 3 is 9. So I'm going to have 90, right? Yep. Okay. So how many? Let's see. Okay. How many sequences of let's see. How about this word? How many, if I have Scrabble tiles like this, suspicious, right? How many scrambles of the word suspicious are there where I take the Scrabble tiles for each one of these and I rearrange them? See if you can figure that out. This is a little, I'm giving you a little bit tricky because there's three S's, right? There's 1, 2, 3, 4, 5, 6. So there's 10 letters. Right? Sam, you understand the problem?
So in parallel, we have two on, right?
Well, we have several different, let's see, there, yeah, there's 90.
Yeah, but like.
3 times 3 is 9. 2 times 5 is 10. 10 times 9 is 90. Because I have these cancellations. Yeah, you can do 15 times 6. But what? Well, I just said 2 divided by 2 is the 1. Okay, so how many well, there's 3 S's and 2 U's and 2 I's, right?
Yeah.
You have an answer? Oh, you have the formula. Okay. Let's see. Well, there's 10 letters. So if we counted them overall, what we do is we do the total number of letters. That's the number of sequences if they're all independent. Then I do the same thing. I divide out by the 2 U's. I divide out by the 2 I's, and then I'm going to divide out by the 3 S's. But it's 3 factorial, right? Because in every sequence, I'm going to have, say, something S1, something S2, something S3, perhaps something, right? And so what I'm dividing out with a 3 is, I'm dividing out by all the ways of rearranging these 3 things. Like I'm going to have 1, 2, 3, 1, 3, 2. You'll have 1, 2, 3, 1, 3, 2, 2, 3, 1, 2, 1, 3. 3, 1, 2, 3, 2, 1, right? 1, 2, 3, 4. Got 1, 2, 3, 4. I have all the different ways. Well, the ways of rearranging 3 things in 3 slots is 3 factorial. So the way you do a scramble of a word is to take it as if they're all independent and then divide out by the factorial the number of letters that repeat. So, for example, you could practice with the word Mississippi, right? That has lots of repeated letters. Excuse me?
Massachusetts.
Or Massachusetts, right? Okay. So that's a version of this first problem. This one? Okay. So here's one. How many scrambles of cats are there? How many scrambles of dumpster? How many scrambles of mama? How many scrambles of Mississippi? Okay. Now what happens though? This is the second sort of problem we're coming to, which is what happens if you have n items, they're all distinct, but you have S less than n slots, right? Let's say that you have 5 items and you only have, say, 2 slots. It's not how you, or sort of locations, 2 slots to put them in, okay? So you only have 2 slots, right? So I can choose any of the 5 here, right? And since these aren't repeated, they're distinct, I can have 4 here, right? So the number of ways, this is the answer, just 5 times 4, right? So the answer is 5 times 4. But we want to write that in a way. What if I had like 100 items and 15 slots? Then I have to write 100 times 99 times 98.
All the way down to 86.
Right, so it'd be a mess, right? Okay, so there's a trick for writing these. What we do is we want to say, well, this is the beginning of a factorial. So we say, okay, well, if we had over here 3 times 2 times 1, right? We could write this as 5 factorial, right? But we don't. So what we want to do is we want to put it in, but divide out by 3 times, but the same thing. So we've multiplied in and divided. So we haven't changed the number. We've just made it look like 5 factorial times 3 factorial. So the number of, if I put 5 items in 2 slots, the answer is 5 factorial over 2 factorial. 3 factorial. Okay. Well, because I want to make this into a factorial. So I want to, if I was to continue this down to a factorial, what I'm missing is 321. So I put it in, but divide it out. So I haven't changed anything. It's a trick, right? So then the answer is 5 factorial divided by 3 factorial. So now if I had 76 items, right? And 2 slots, then I can see I'd have 76. That would be the answer, 76 times 75, right? But then what I'm missing would be 74 times 73 to 1. And then I have to divide out by 74 times 73 times 2 times 1. But that equals 76 factorial over 74 factorial. And you notice the pattern here. This is 2 less than the 5, right? So it looks like the pattern is n factorial over n minus s factorial, right? Because you can see here, if the number of, we could test this out by doing, say, what if I have, say, 7 items and 3 slots? Okay, so I have 3 slots and 7 items. We have 7, 6, 5, right? So the answer is going to be 7 times 6 times 5. But then what I want to do is multiply in the piece that's missing, 4 times 3 times 2 times 1, divide out by 4 times 3 times 2 times 1. So you can see the answer is going to be 7 factorial over 4 factorial. And that's the same thing as 7 factorial over 7 minus 3 factorial for the 3 slots, which is 7 minus 3 is 4. So that's the same as this formula here, right? N factorial over n minus s factorial. That gives you, this is the piece that you multiplied this in to make it look like factorials. So you don't have to write out like lots of numbers. So it's a trick for counting things when if you didn't use factorials, it would be too many numbers to write. It'd be very confusing to look at. Okay. So that's number 2, the copy of n items with s less than n, fewer slots than items. And it goes through, and there's the formula there, right? And some examples. But what happens if we have, let's go to the next one, number 3. What happens if we have n items and s slot, but we have as many copies of the items as we want, an inexhaustible supply? Well, if we have like, let's say we have like 7 items and 3 slots, right? Well, that just means we can put any of the 7 items here, any of the 7 items here, and any of the 7 items here. So the answer is going to be 7 times 7 times 7, which equals 7 cubed. Well, you can see that the answer is going to be n items raised to the power S.
That's what.
This is when they're replaceable. You can, this is when you have as many as you need. Now, that's what we want to do with sequences, right? But there's another one, which are these were counting arrangements. And now we're going to count combinations. Think of this as teams. Let's say you have 10 people and you want to choose a team of 5 people. Well, you're not choosing a sequence. If the 10 people ran a race, then the people who came in first, second, third, fourth, and fifth place, you'd want to know how many sequences. Like the 5 people could come in first place, then 4 in second. So that would be like counting sequences. But we want to count, if you have 10 people, how many different teams could you make by choosing 5 for a 5-person team, right? So these are combinations. That's what we mean by the word combination. So let's say, well, let's do that case. Let's say we had 10 people and we want to know how many teams of, let's say 4 people. 4 people on a team. How many ways can we form a team with 4 people of this, right? Well, here's the way to do it. You have four sort of positions on the team, right? So let's say that we're counting sequences. Let's say we're counting the order we choose the people in the team. I could choose any of the 10 people first, right? Then I could choose, there's 9 people left. Then after those 9 people, there's 8 people and 7, right? So this is the number of ways of choosing 4 people. But the problem is, so for example, I could have let's say the 4 people are A, B, C, and D. I could have chosen A, then B, then C and D, or I could have chosen B first, then A, C, D, and that would be the same team, just mixed up members. So what we're going to do is we're first going to write this number of the sequences in terms of factorials, right? We're going to say the number of sequences is going to be 10 times 9 times 8 times 7. Then we add in the 6 times 5 times 4, 6 times 5 to 1. And that's going to equal 10 factorial over 6 factorial, okay? That's the number of sequences or arrangements. But we've overcounted, right? Because there's 4 items and they could be in any slots. So the thing is, since how many, for every arrangement, how many different ways are there? Well, I could have chosen any of 4 people here, then 3 and 2 times 1. So I'm going to take this number and divide out by 4 factorial, just like I did before when we had the letters and we divided out by the overcounting. We've overcounted by counting sequences. Since all 4 members are equivalent for different slots, it's as if they're all identical. I can divide out by the 4. So the answer is, if you count combinations, if I have n items, divide up into it, and I have s positions on a group, how many groups of size S? If I have n items, how many groups or teams of size S can I choose? It's going to be n factorial over n minus s factorial. This is the number of sequences divided out by s factorial. Okay, this is the method. By counting sequences, I've overcounted. This is the number of dividing out that overcounting. So, for example, if I have 7 items and I'm going to choose four positions or 4 items on a team, I'm going to have 7 factorial over 7 minus 4, or 3 factorial times 4 factorial. And you might recognize this, well, there's two things. This is also called a binomial coefficient because of the way it came about in counting terms in polynomials. The name isn't important because we just think this is the way of counting groups or sequences. It also has a name. Sometimes this is given the name of n, s, and this is read, given n items, choose s of them. The number of, so this symbol represents the number of ways of choosing s. If you have n items, choose how many ways can you choose s of them. So this is the story. Okay. So that's if all the items are distinct, and we go through and it goes through this definition here, and they're called binomial coefficients. Okay. So that's about that's the story. Those are the formulas that you use. So the important thing in problems is recognizing first, are you counting sequences or are you counting combinations? So I could ask one problem or the other, and you don't want to do the formula. You want to get the right formula, right? And sometimes you need the method of getting it, right? So we're almost out of time, but I wanted to go, we have some more sections here we'll get to on Friday, and we'll then do it. But there's a project at the end for counting birthdays, okay? So this is a project for you to sort of solve, right? So let's look at, so you guys over there are, okay, counting birthdays, right? This is the project at the end of the chapter. We only have 2 minutes, just your attention for 2 minutes, okay? So we're going to use the results of this chapter in the next chapter on probability. So the question is, how many ways are there for one person to have a birthday? Yeah, because there's 300. Well, we're going to forget leap years, right?
Yeah.
Okay, let's say that they're forgetting leap years, where someone can be born on February, what, 29th or something.
What time?
So yeah, because you could be born on the first day of the year, the second day, or January 1st or December 31st. There's 365 days in the year. So that means there's 365 different birthdays. Right? So if someone came in and you were to guess their birthday, there'd be like 365 possibilities, right? Okay, how many ways are there for 2 people to have the same birthday? Yeah, because they both have to have the same birthday, January 1st or January 2nd. Okay, well, how many ways are there for 2 people in a group of n people to have the same birthday? That's a little more difficult, right? So if you ask, like, let's say I have 10 people, and I want to know how many ways are there for 2 people, at least 2 people in the group to have the same birthday. Well, there's a complicated problem because you could have different people could have the same birthday, and they could be in different days of the year, right? So it's going to be easier to ask a different question, right? How many ways are there for at least 2 people? It's difficult to ask a different question, number 4 here. How many ways are there for at least 2 people to have different birthdays? That's an easier question because, okay, the first person, where could they be? How many ways for the first person? 365. How many ways for the second person if they can't have the same birthday? 364. So the total number of ways they could be different would be 365 times 364. So then the question is, how can we answer question 3, given that it's relatively easy to find the answer to question 4? Well, if we think of, let's think of the set of all the different possible ways of 2 people having birthdays, right? It divides into 2 pieces. Those where they have the same birthday and those where they have different birthdays. Those don't overlap, right? So if you add those up, they add to the total number, right? So if we have sort of, there's A and B, we figured out A, we want to find B, but A plus B equals the total number. So if we figure out the total number, so how many is the total number of possible birthdays that two people could have?
Same. No, the total minus the.
No, just think of it as a separate question. How many ways could, if you don't care if they have the same or different birthdays, how many ways could the first person have a birthday? How many ways could the second person have a birthday? And what's the total number of ways?
365 squared.
Right, 365 squared, because they're independent choices. So if I take A plus B equals the total, I can subtract 1 to get the answer. Okay, now the real question is, how many ways are there for n people to have different birthdays? Right? Let's say I have a group of 50 people. Well, the question is, how many ways are there for 50 people? Let's say I want to know, out of 50 people, how many ways are there for there to be at least a pair of people to have the same birthday? At least 2 people to have the same birthday. So if I figured out everyone's birthday, I'd know how many people have the same birthday. Okay, well, this is leading up to the question. What you want to know is, you want to be able to answer this question: how many ways are there for n people to have different birthdays? Right? Because we want to know the flip side. So solving this counting problem will help with the next chapter on probability, because then we want to know, we want to calculate what's the probability, how the likelihood, we haven't defined probability yet, of 2 people having, if let's say I have a group of 50 people, what's the probability that 2 of them have the same birthday? It's a thing that's used at conferences as an icebreaker, right? Because what the person will do is they'll have everyone, say in a group of 100 people, write down their birthday, not the date, not the year, just the birthday, and then they'll take those up, and it'll be guaranteed, he'll know with a certain number with a high probability that at least 2 people are going to have the same birthday, so we can ask them questions, anyway. So it's something that you expect is not, there's an upper limit though. How many people do I need to be guaranteed 100% of the time that I have 2 people with the same birthday? That's a pigeonhole problem, right? How many ways?
364.
364, but I could put them all on different days of the year.
366.
Yes, 366. Because you put one person each day of the year, then the 366 person has to go on one of those days, which someone, unless they've been born in a leap day. Okay, we're out of time. People really in the Middle Ages, there was a problem that was out of sync, and they had to then introduce a different scheme. They had to sort of take off a bunch of days to to adjust the schedule, and everyone complained that they were going to be younger because they wouldn't be able to have their birthdays. So they objected to changing the calendar because they didn't want to lose their birthdays. And it's the same problem with someone who's born in a leap year. If they only have one calendar birthday every 4 years. So they could, so I think there's an actress who was born on the leap day, and so she only has her 21st calendar birthday when she's 84. So.
Divide the person's age, it's like a leap year, you divide something with age by 4.
Yes, more or less. It's a little bit more complicated because there's it's like leap years aren't every 4 years. They're every 4 years unless it's like 100 years.
Yeah. And
then, but except for the fact if it's 400, it's divided by 4, then you go back and so it's like this complicated formula, because otherwise the calendar gets out of sync
Yeah,
with the,
yeah, I have a cousin like that. I think it's celebrating his birthday. We used to celebrate it every year, but now it's pretty good.
yeah, you could actually only have it on the birthday every, fourth year.
We would do it every year, like
So then you only have to put four, when he's like 4 times, when he's 16, you only need 4 candles, right? So you finally made it up to being a toddler, you're 16.
Yeah.
Yes.